Hey everybody, and welcome to my first video, and I'll be going over all the 2020 USAPhO problems in a video series. And unfortunately, due to the COVID-19 pandemic this year, as many of you might know, the 2020 USAPhO has been cancelled along with the annual physics camp that they hold in order to choose the attendees to the International Physics Olympiad. But obviously everything has been cancelled and screwed up due to the COVID-19 pandemic. But in any case, I'll be going over the problems that they gave out as the 2020 USAPhO. And if you want to check out the paper, if you want to open it up, as you can see, I already have A1 written out. I have all the details written out. But you can go to AAPT Physics Team 2020. Search that up on Google. And once you're on the website, there should be a sidebar, and on that sidebar you can click News. And from News, that's where you can scroll down and you can find the solutions and the problems for the 2020 USAPhO. But actually, as it's been pointed out in many occasions that you might have heard, there were several errors with the solution that was posted online. So I'll be also going over that, and perhaps we'll get started now. Okay, so let's take a look at problem A1, breaking up. An infinitely long wire with linear charge density negative lambda lies along the z-axis. So as you can see, we have an infinitely long line, and an infinitely long insulating cylindrical shell of radius a is concentric with the wire and can rotate freely about the z-axis. The shell has the moment of inertia of unit length I. Okay, well, so there's your shell, and it's telling you that it has a moment of inertia I and a charge density lambda over 2 pi a, surface charge density. Now, also it says that the system is immersed in an external magnetic field B naught times z hat and is initially at rest. And if you're not familiar with this notation, z hat is essentially referring to the unit vector in the z direction. So as you might know, in 3D Euclidean space, there are three coordinates, so x, y, z, and the basis vectors for the Euclidean space are x hat, y hat, and z hat. You might have seen I hat, j hat, and k hat somewhere, but this is for general spaces. But for Euclidean space, you can use this. And so basically, this is just telling you that your magnetic field is only directed in the z direction. So what happens? Now, what's the next part of the story? Starting at t equals 0, the external magnetic field is slowly reduced to 0 over a time t is strictly greater than a over c, where c is the speed of light. And it asks, find an expression of the final angular velocity of the cylinder in terms of the symbols given and other constants. Okay, so how exactly could you even start this question? Well, the first thing to notice is this changing magnetic field. Well, as you can see, this magnetic field is changing from a value b naught to 0 over a specific time t is strictly greater than a over c, which means a pretty sufficiently long time interval. Now, what's exactly happening? Well, this changing magnetic field might remind you of something called Faraday's law, or even Lenz's law if you've heard from your AP Physics C class. And from there, what it tells you is that this magnetic field induces an electric field. And this electric field, and so there's a magnetic field in this positive z direction. So where exactly are the electric field lines located? Well, this electric field is going to be in kind of concentric circles around, so if you can visualize this better, so this electric field will be pointed in concentric circles around this wire, around the magnetic field lines. So whenever you have a magnetic field line, the electric field line is going to be pointed concentric circles. So in that regard, well, then we know that this electric field will pose some sort of torque, will apply some sort of torque to this system in order for it to, and that will be the cause of this, angular velocity omega. So these electric field lines are applying a torque to the system, applying a torque to the cylinder, which is therefore causing a induced angular velocity on this cylinder. Now, so let's get started. So I'm going to start with writing out the torque equations. So as I said, I'll just write this out over here. I'll go over here in blue. I'll just write this concentric circle stuff, and I can tell you that these are your electric field lines, and I'll call this E. I'll just call this E. Okay, so E induced. Okay, so E induced is your electric field lines around that are causing this torque. So let's go and write this torque equation at the bottom. So let's go to A, and I'm not going to write it like a full solution. When you're on the actual test, you can write out everything that I said, explain it fully, but right now I'm probably not going to do that for the video, so I'm just going to write it out for you guys. So as you know, torque is equal to I alpha on the cylinder, right? So this I alpha is also equal to the force times the moment arm, as you know from your physics class. So what exactly is this torque? And what exactly is the force that's being applied? Well, as you know, force can be equal to Q times E, where E is the electric field, right? So Q can be expressed by this charge density. So your charge density, lambda over 2 pi A, times it's your surface charge density, so you're going to have to multiply this by 2 pi A to get your total charge, right? Now that times your E induced, and this should also be, so E induced times your moment arm, which is A. And so these cancel out, and that leaves you with just lambda A times E induced. Okay, so now this raises the question, exactly how do you find this E induced? And that's the next question that we're going to be discussing right now. And so the answer to that question is by using Faraday's law. And so Faraday's law of induction. So what is this state? And let me just zoom in a little bit so I can write a little bit neater. And I'll share these notes on my YouTube description later on, so you guys can check it out. Just law of induction, not laws. So what exactly does this state? Well, this states that the integral of the electric field dl, this integral right here, is equal to negative d phi b dt. So what is this stating? Well, what it's stating is that the electric field, this integral of the electric field, is equal to the this line integral of the electric field is equal to the negative derivative of the flux of the magnetic field. And we can prove it, but we'll save that proof for another day. But we'll just apply this. So this is E induced. This is exactly what E induced is. Okay? Now, how exactly can we apply this formula? Well, let's look over here. I'll write this in black and then underline it in orange. So I'm going to write the formula again, right? So E induced times, or dot dl, because with vectors, so that's equal to negative d phi b dt. Now, what to do here? Well, what we can do is, we can technically factor out this E induced. And this gives us, and what is this flux equal to? Well, it's just area times the magnetic field. So it's just going to be pi r squared. Well, we'll consider E induced of r. So let me just grab this. Remember, this E induced is going to be a function of your radius, or however, however far you get from this line. So just say this like r right there, if you get what I'm saying. So now that's times dB dt, because you're left with your derivative of the magnetic field. And how exactly can you integrate that? Like, what the hell is this like circle in the in the integral doing? Well, what that exactly is saying is that you're integrating about a closed contour. And so what's happening is that you have this circle that you're integrating upon right here, right? And so this circle is of radius r. So what this line integral is saying is that, oh, okay, well, I want to integrate about this entire circle. So if you're integrating about this entire circle and you want that integral of dl, well, that's just going to be the area of that circle. So this, what exactly this is just, take a guess, it's just 2 pi r. So therefore, we finally get that the E-induced function as a function of r is equal to negative r over 2 times dB dt. So let me just underline this entire thing in orange so that you know that this is referring to Faraday's law. Again, I'll post everything on my YouTube channel description so you know exactly what's going on. And you can refer back to these notes later. And so if you want just an aerial view again. Okay. Now that we're done with that, we're going to substitute that into here. And remember, this is a E-induced of A, because we're talking about A, right? So let's just substitute that in. And we get that, and we want to find the final final angular velocity. So what we do is we have I alpha is equal to lambda A times negative r over 2, well, in this case, negative a over 2, times dB dt, and that finally gives us that the angular acceleration is equal to negative lambda a squared over 2I dB dt. Now, how can you express this in terms of angular velocity? Well, this is just d omega dt. So that's how we're going to express that. And then, oh, hey, look, we have a differential equation. Yay, right. So now we can integrate both sides. And we can therefore get that, and remember, in this case, that remember your bounds, right? So you're integrating this from this dt, right? From 0 to t, perhaps. This from 0 to t, if that's making sense. So I'm going to pull this out again, just show you exactly what I mean. Let's see how we can do this. Okay. Yeah, this app is really useful. If you want this app, you can ask me in the chat, but whatever, we'll see. So d omega dt times the integral, so that you're integrating over time. And this you're integrating over time as well. You have negative lambda a squared over 2, I believe, yeah, 2I dB dt times dt. And that finally gives you an equation that states that omega t, so remember, your omega of 0 is 0 because it's not even rotating when your time equals t, when t equals 0, right? Because nothing's happening. So that's equal to negative lambda a squared over 2I times b of t minus b naught. Right, so because your b of 0 is just b naught, which is your initial, initial magnetic field. And that's changing over time, so yeah. Okay, so there's another problem. How can we find b of t? Like, what the hell is b of t doing, right? That is your next question. That's what your next question should be. Well, this b of t can be calculated with Ampere's law. So what's going to happen here is that we need to find this induced magnetic field. So what we can do here is b of t can be calculated with Ampere's law. And so what does Ampere's law exactly state? So we'll use orange to denote theorems. And so Ampere's law, so it states that the magnetic field in a closed loop is equal to mu naught, which is the magnetic permeability constant, times I enclosed. So this is exactly how we will go about finding this magnetic field. And so what exactly, in order to find this line integral right here, we have to choose a proper, contour, a proper loop for us to integrate upon. Well, so what exactly should that contour be? So if you remember, maybe from your AP Physics C class, what exactly was the line integral what exactly was the contour that that you used when learning Ampere's law? And that might remind you of a solenoid. And so a solenoid, what you had was a bunch of wires, and the magnetic field you have a loop of wires, and the magnetic field goes straight through, right? And what you did was you took an Amperian loop, and that would be a loop of length L, and the magnetic field outside would be 0, and the magnetic field inside you'd have to calculate, and that's how you derive the formula for the magnetic field inside an Amperian loop. Inside a solenoid. I'm going crazy. Well, anyways, so that's how you do that, right? So in this case, it's literally just the same thing. We just have to take, a rectangle of length L, and that's going to be your Amperian loop. And so that's what we're going to be, performing our integration upon. So we have, you can consider, this to be your loop that you're integrating upon. Okay, so now that we know that it's a rectangle, let's get started on, solving it. So let's go back to orange, or black. Okay, so what is your B of t? So the integral, of this is equal to mu naught times I enclosed. What exactly is I enclosed, though? That's just equal to your current, right? Which is equal to your change in charge over time. So that's just, you can consider that to be dq dt. Right. Okay. So since your charge is going to be changing linearly, we can just consider this to be, delta q over delta t, and that makes it much easier for us, and I'll tell you exactly why. The reason for that is because this delta t can be replaced with 2 pi over omega, because your delta t is essentially your period of your the period of your rotation. So if you remember from simple harmonic motion, perhaps, that t is equal to 2 pi over omega, this is in the same way that you're just substituting 2 pi over omega for the period. Now, what's your delta q, your charge? Well, that's just equal to lambda over 2 pi a, your charge density, times your area, right? So that's 2 pi a times L. So that's your area. Right? Charge density times your area. Okay. Now, what exactly is this side? Well, this side just evaluates out to b times L. So that's just your integral for that loop, right? Simple enough. So this is just b times L is equal to mu naught times lambda over 2 pi a times 2 pi a L times omega over 2 pi. And remember, this is omega of t, so you just keep it in mind. Oh, sorry. And don't worry, the other parts shouldn't take much time, and so this video might, go on for another 10 minutes or so. So you can cancel these out, you can cancel this out, you can cancel this out, everything cancels, and we're having fun, right? So that means that we have, finally, that b is equal to, b of t is equal to lambda over 2 pi times omega of t. And everyone's happy because you have b of t as a function of omega t, so therefore you can plug it all in and get your final answer. So what you get is your final answer is that omega t, and you can see this, and you can just do the algebra out. Omega of t is equal to a squared lambda over lambda a squared over 2i. Let's just see this again. Negative of this times lambda over 2 pi omega of t, and that's plus or minus b naught. And simplifying this out, we eventually get that omega of t is equal to lambda a squared b naught over 2i, that all over, hold on, let me just pull this up for a second. Hopefully I didn't make an error in my algebra. Negative, and then you add it on the other side, lambda squared a squared over 4 pi I plus 1. And so that should be your final answer. So let me just draw an arrow there, and I'll highlight it so you guys know that is your final answer. Cool. So we just have finished part A. Now part B and part C are relatively much simpler, so we can quickly go over them. So let's go. So let's move on to part B. And so what does this say? So you may be surprised that the expression you find above is not 0. So let's first discuss exactly what's going on here. So what happened here? Well, this they're looking at it mechanically, right? The angular momentum, you may think is not conserved, right? Because there's an angular momentum there's zero angular momentum before, and now all of a sudden you have this angular momentum omega, and it's rotating this cylinder. So it may seem like this angular momentum is not conserved, but in reality, the angular momentum is conserved because the EM field also has an angular momentum to it. So light has an angular momentum. So that exactly is characterized by these two set of equations that they give you. And this is what they're telling you. They're telling you that there is an intrinsic angular momentum to the EM field, and therefore there is angular momentum conservation in this problem. And so that's exactly how we solve this expression for alpha in part B. So we have to do angular momentum conservation and equate these two angular momentums that we find before and after. And that's the point of this problem. So that's exactly what we're going to do in order to solve it. So what exactly was going on? So let's do these. Sometimes these cross products might be a little scary or tricky for you. So we'll go through them a little bit and see what you guys think. So part B. So we have this angular momentum r of an E field is equal to r times this fancy p times r, p of r, right? And p of r is basically your linear momentum, perhaps, of linear, quote-unquote linear momentum, and that's defined in terms of your pointing vector E cross B, and this is known as your pointing vector. It tells you the intensity of your EM field, and you can look into it on Wikipedia or something, and it's kind of interesting, and it has many applications. In any case, we'll keep moving, and so first step, calculate this angular momentum so we can use angular momentum conservation. Right, this is angular momentum per unit volume, so we're gonna have to work around that too. So let's first do this. So this is quite an interesting problem, but not that difficult. So let's first go through this very quickly. So P of R is simply equal to alpha times your electric field. So what exactly is your electric field here? So you may think, okay, well, your electric field is your electric field given by a cylindrical shell. And so that is namely just your lambda over 2 pi, I'll write this on here. So this is just lambda over 2 pi epsilon naught r times r hat in the inward direction. This is just saying that you have your basis vector. This is in polar coordinates. So r hat is just your so when you have polar coordinates, you have your theta and you have your r component, and your r component is directed, it's telling you that you're directing it inwards. So this is your electric field, and your magnetic field, well, the negative is telling that you're directing it inwards, but this is your radial component. That's exactly what I'm trying to say. So r hat means radial component. So well, the magnetic field exactly is B times z hat, right, as we have right here, so right there. Okay, so well, this varies technically across time, right? So you can say B of t z naught, z hat, right? So now let's do this cross product. Yay. So now let's get to doing the cross product. Negative lambda over 2 pi epsilon naught, 2 pi epsilon naught r times b of t, then times r hat cross z hat. Now, you may want to familiarize yourself with these cross products of basis vectors, and what this exactly gives you is your theta hat vector, which is your basis vector this is your second basis vector in polar coordinates. So exactly what's happening is that p of r is equal to alpha, or negative lambda alpha, over 2 pi epsilon naught r times b of t times theta hat. So that's exactly what's happening here. Now, let's plug this into your first formula for angular momentum. Right, L of r. So I'm getting a little lazy with my drawing. Maybe I'll organize it up before I send it on the description. But L of r is equal to negative alpha lambda alpha over 2 pi epsilon naught r b of t, and then you have your theta hat cross your r hat. This gives you z hat. Okay, so now we have our angular momentum here, and we're just going to do angular momentum conservation. But remember, be aware, this is L of r, and that means that this is your angular momentum per unit volume as it tells you. So this means that you'll see exactly what we're going to do quickly. So angular momentum conservation. And I hope this is interesting to you because, this concept of angular momentum, this electric field having an angular momentum, intrinsic angular momentum, is really cool because you might think, like, initially, oh, hey, this is such a, apparent violation of angular momentum conservation, but it really isn't, and I think that's pretty cool. In any case, so let's move on. So, let's do angular momentum conservation, and let's just say Li is equal to Lf, right? But we have to be careful because this is per unit volume, and we just want to make sure that we get this right. So Li is, only angular momentum is provided by your B field. So your B field is just, not the B field, but by this thing, right? So that, we'll shift into per unit length rather than per unit volume. So what we have is, we have negative lambda over 2 pi epsilon naught r times b naught z hat times alpha, right? And so that's your initial angular momentum. That's it. So that's equal to Li. Now what's Lf? Lf, well, we have our negative lambda alpha over 2 pi epsilon naught r b naught z hat. Oh, I forgot to tell you something. Because we want unit volume, we want unit area. Sorry, we want unit length, right? So we're going to multiply that by the area, which is pi r squared. This cancels, and that gives us lambda alpha b naught over 2 epsilon times r in the z hat direction. So this is also times pi r squared in the z hat direction. But we also obviously have our, angular momentum due to the cylinder rotation. That's just I omega of t times z hat. And actually, I made a mistake right here. This shouldn't be, just drag this out a little bit. Oh, sorry. So that should be b of t. I'll just drag this back. Okay, so now that we have this, what exactly is I omega of t? Well, we already calculated that from our previous problem right here. So what I'll do is, I'm just going to directly copy this formula, just like that. And so what we get is the following. Well, the i's cancel. So the i's cancel, you're left with 2 on the bottom. Right? And so from there we can set them equal to each other. But remember, the omega, this omega right here is not per unit length. So we have to shift that into per unit length, right? So to make that per unit length, what we have to do is, oh, sorry, this is the wrong formula. This is for the B field. Yikes. Okay, so you can go right here, I guess, and copy and paste this formula. Right here. There we go. That's the right formula. Okay, so yeah, so actually this is fine. So we have this cancellation of angular, this moment of inertia, and so that's going to be right there, times obviously z hat. All right, well, there you have it. So now we're just going to simplify everything. So this is just this. So these two are equivalent. And so now we're just going to simplify everything to find our alpha. So combining everything, this gives you negative lambda alpha over 2 pi epsilon naught r. And this is all z hat, so I'm just going to ignore the z hat and just so we can find the quantity. So b naught minus equals negative lambda over 2 pi epsilon naught r, b of t, then plus this one. I'm gonna grab this one and put over here. Gosh. So now that's minus that. And so what we get is that at last we get that this, you can switch this around. So at last you finally get, solving this equation. It's going to tell you the answer. Alpha is equal to epsilon naught. And that is your final answer. Okay. Well, thank you so much for watching. And I'm going to upload these notes onto the YouTube description. And thanks so much for watching, and hope you have a good day. Bye-bye.